Thanks, everybody, for coming today. Those here in person and on Zoom. This is one of our many lectures that we have every year, the Emeritus Academy. I'm T.K. Daniel, chair of the Academy. And we have a wonderful presentation today. Before I get into that presentation, I want to make one announcement for next month, April's presentation. It's called Harry Potter, Rule Breaking and Political Resistance. Emeritus faculty member will be Beth Sutton Ramspeck. Her presentation, she's going to give the presentation on Zoom. I think she's out of the country, if I'm not mistaken. Oh, she's in North Carolina. But we will have in-person seating as we have now, as well as on Zoom. And the time is going to be different. Instead of 4 to 5, it's going to be from 3 to 4. Okay. Now, to the headliner today. Larry Krissek, an emeritus professor in the Department of Geology, Mineralogy. He also served as vice chair of the department for 20 years. After retiring in 2017, he was rehired for 2 years as associate provost and continued to work on university-wide review and revision of OSU's general education requirements. In 1998, he received the OSU Distinguished Teaching Award. And in 2015, the University Distinguished Service Award. Dr. Krissek's primary research interests are in the study of the evolution of climates and ocean environments on the Earth during the past 65 years. These interests have led to participation in 9 field seasons of research in the Antarctic, plus 2 years leading an OSU study abroad class to Antarctica, and to participation in 9 cruises of the various programs of scientific ocean drilling. He is presently involved in 3 major activities: chairing the Joint Oceanographic Institutions for Earth Sampling. By the way, that's a 6-digit acronym. Resolution Faculty Board, the Advisory Committee for the U.S. vessel used in scientific ocean drilling, and heavily involved in planning for the next phase of U.S. scientific ocean drilling. Secondly, writing, co-editing an introductory level text on the geoscience perspective on climate change. And third, working with the education group of the USDA-funded Smart Foodscapes project based out of Utah State University. He also serves as a consultant to the Ohio Department of Higher Education, especially around the implementation of a DEI option within the Ohio Transfer 36 program. His lecture title today is Scientific Ocean Drilling, 50+ years of scientific advances and international collaboration, but an uncertain future. Larry? All right.
Thank you, TK. And thank you everyone for joining here in person, or for those of you who are out in Zoom land. The one thing I would say about those of you in Zoom land is if I'm using a pointer, it's going to be a laser pointer on the screen here. So I apologize, you won't be able to see that on your screen. So I'm going to be talking about a series of projects, international projects that have taken place over the last 50+ years. A number of people in this room, in addition to myself, actually have been involved with various parts of these projects over the years. This is not something that necessarily comes onto the OSU radar screen very often, but there are some of us for whom this has been an important part, really, of our careers. This is something I have been involved in basically all of my career here at OSU. The ship that's shown on this slide is the JOIDES Resolution, which is a vessel you'll hear more about. It has been and it continues to be the workhorse of scientific ocean drilling. But unfortunately, it is a vessel for who the future is quite cloudy. This particular photograph was taken in Yokohama in 2009. And although it's hard to tell from the configuration here, when this vessel goes into Yokohama or tries to access certain other areas, the fact that there's a 220-foot tall drilling derrick limits where it can go. So you see the bridge in the background. In Yokohama, this vessel can only dock in the outer portion of the port because it can't get underneath that bridge. And there are other times when the derrick, which is essential for the work we do, has introduced some challenges in trying to move the vessel around. So a roadmap for the talk today, 3 parts: a brief history of scientific ocean drilling. Then we'll talk a little bit about how the present program works, and then the outlook for the future. That's the place where lots of uncertainty will appear on the horizon. So scientific ocean drilling has really consisted of 5 separate projects over the space of the last 50 to 60 years, depending on when you want to count the start. So beginning with what was called Project MOHOLE in the late 1950s through the mid 1960s, that we'll see didn't really provide much scientific background. It was basically a proof of concept about the fact that you could actually do drilling in the deep ocean. Then the deep sea drilling project from the late 1960s through the early 1980s, using a vessel called the GLOMAR Challenger. Then we moved to the ocean drilling program, which began to use a different vessel, the JOIDES Resolution, which I've already shown you a picture of. And I'll let you know, in the community of those of us who use it, the JOIDES Resolution is just referred to as the JR. So when I call it the JR, that's what I'm talking about, the JOIDES Resolution. And then we moved in the early aughts into the integrated ocean drilling program, sometimes referred to as IODP-1. And then we transitioned to the same acronym, but different words. So notice we stopped being integrated and we went back to being international. We took drilling out of the name because this renaming was shortly after the Deepwater Horizon event in the Gulf of Mexico. So having drilling in the name was seen as a bit of a PR oops. So we're still IODP-2, but that's the International Ocean Discovery Program. Now, according to the original funding, IODP-2 was scheduled to end as of the end of this fiscal year 23. So it would have ended at the end of September 2023. But because of the various complications on activities that arose from COVID, the various funding agencies agreed to a 1-year extension. So IODP-2 continues till the end of September 2024. Beyond that, the world gets very cloudy, as we'll talk about in a little while. Okay, just a little bit of a sort of the highlights on the various parts of our history of scientific ocean drilling. Project MOHOLE. This derived its name from a goal of drilling to what is known as the Mohorovicic discontinuity, which is thought to be the boundary between the crust and the mantle. That is often shortened and talked about as the MOHO. So this was intended to be a drilling to reach the MOHO. The reason you would do that in the ocean rather than on land is that that boundary is much, much, much shallower beneath the ocean basins than it is beneath the continent. Now, I haven't looked back into the archives, but the story goes that the inspiration for Project MOHOLE was, it was 10 guys 10 guys, sort of the grand old men of the discipline at that time in the late 1950s, sitting in a bar. And after a few drinks, this got sketched out on the back of a napkin. They felt that they needed to have a name when they went to the funding agency, so they anointed themselves as the American Miscellaneous Society. And that was how the proposal went to the funding agency. They got funding. They had funding for a vessel. Oops, sorry. I'm trainable. The Cuss 1 seen here on the left. That vessel, I have no idea what's happened to it, but what I will point out is that there are a couple of elements that you see on Cuss 1 that if you've never spent much time looking at ships, thinking about ships, you will see that these are common elements continuing on to the JR and the other vessels that we use. The first is the presence of the derrick, this tall structure in the middle of the ship. That is designed to be able to allow you to take long pieces of drill pipe, move them from their horizontal stacked position, make them vertical, screw them together, and then lower them down. What you can't see is that immediately underneath the derrick, there is an intentional hole in the bottom of the ship. That's what the drill pipe goes through as it goes into the water. That's referred to as the moon pool. The other thing that is a common element we'll see on other vessels is this pile of drill pipe in the back. Those are in industry standard drill pipe, 90-foot lengths, threaded on each end. Those are pulled forward, taken up into the derrick, lowered down, screwed together. That's how you put together the drill pipe. As the drill pipe is assembled and goes into the water, we call it a drill string. So if I happen to talk about the drill string, that's the assembly of these pieces of pipe that will go from the vessel down through the water to the seafloor and then into the seafloor as we drill. Probably the biggest achievement from Project MOHOLE that influenced the history of scientific ocean drilling was demonstrating that it was possible to keep a ship in one location without having it anchored to the seafloor. This is what's called dynamic positioning. In the water depths that we're talking about, half a mile, 2 miles, 3 miles deep, you can't put down an anchor and hold the ship in one place. So this has to be done in some kind of a triangulation system and then using thrusters that allow the vessel to move sideways. And so this was a proof of concept first demonstrated during Project MOHOLE. Okay, so Project MOHOLE demonstrated that deep water drilling was viable, but had limited scientific outcomes. We then turned to the second of these programs, what's called the Deep Sea Drilling Project, which operated from 1968 to 1983, using a vessel we'll see in just a moment called the GLOMAR Challenger. For the first 5 years, DSDP was funded only by the US. For the subsequent 10 years, it was international. And that history of international cooperation has continued to our efforts today, and we hope to our efforts into the future. All right, on the left, we have a photograph of the GLOMAR Challenger. This vessel was about 300 feet long, so about the length of a football field, drilling derrick about 200 feet high, something like that. In this case, the drill pipe was actually stacked up here forward of the rig floor, so it would be pulled back, but the general idea was still the same. A little bit on the name, GLOMAR Challenger. GLOMAR is a contraction of Global Marine, which was Howard Hughes's drilling company. So his drilling company supplied this vessel. The name Challenger was derived in honor of a British vessel called the HMS Challenger that in the 1870s conducted a 3-year cruise all around the world. And that is widely accepted as the start of oceanography as a distinct science. I also want to note, especially for comparison to some things we'll talk about later on, the GLOMAR Challenger went from plans on somebody's desk to a vessel in the water and operating in 2 years. Just to let you know, the punchline at the end, if we're talking about getting a new vessel for US scientific ocean drilling, the timeline is 10 to 15 years. So it's amazing to think about a vessel going from plan to operation in 2 years. Okay, a few of the sort of highlights on the logistical technical side with respect to DSDP. It really, it established a a situation that a number of us have experienced is that we go to sea on these, we expect to go out for 2 months. That's the standard working length. And the reason for that is that not for the scientists, it's for the ship's crew and the technical crew. There's an A crew and a B crew. And over the course of a year, for them to each get equal time on board the ship and back at home. If you subdivide it into 2-month-long segments, everybody gets 3 segments on ship, 3 segments off ship. And they do, if you start thinking about equitability, they do have a situation. So every few years, the crews will run, one of the crews will double up, go back to back, so that then you have the months that you're away and the months you're at home get switched. That way, you know, somebody isn't always missing the holidays, or they're not always missing their anniversary. They get an offset every few years. Okay, so it established a standard of 2-month-long cruises, which has persisted at least for the JR up to today. Really started the world of big science in the marine world. So there were administrative offices that were at Scripps Institution of Oceanography in San Diego. It also established standards for how we handle core. Just to let you know, on another slide or two down the line, you're going to see a number that says during the 15 years of DSDP, there were 19,000 cores collected. Now, a core in an ideal case is 9.5 meters long. You can't move a core that long around on a ship through narrow doorways and things like that. So the core actually gets sliced into 1.5 meter long pieces that are sections. As soon as you start thinking about 19,000 cores times 4 to 6, you know, you're talking about 50,000 to 100,000 sections. Having the equivalent of librarian is really important so that you can keep track of what came from where, what their order is. And for some of us, it's really important to know which is the top and which is the bottom of each section. We don't want to flip them upside down. So a lot of standards for how the cores get handled. Also a number of technical advances during DSDP. They developed the ability to actually pull out of a hole if a drill bit was worn down, pull out of the hole, change the drill bit and go back in. Otherwise, you're never going to get deeper than what you can go with a single drill bit. Sometimes it takes a couple days to get back in the hole, but if it's an option of a couple days or having to start again from scratch, you spend the couple days. Also, the development of some tools that were important for allowing us to sample softer sediments as opposed to the very hard rocks. You go at soft sediments with the standard rotating drill bit, all you do is turn it into a geologic milkshake. And that's of no help to us in the work we want to do. Also, they developed the first options for intentionally leaving instruments in the borehole. We have lots of ways that we can unintentionally leave instruments in the borehole. That happens regularly. Sometimes it's a really bad thing to have happen. But to actually put instruments in that could then make measurements, and the data could be downloaded later if you revisited the site. Okay, so a lot of sort of technical and administrative things. 624 sites visited over the 15 years. These are all shown. What you'll notice is that the vast majority of these are at low to mid latitudes because the vessel was not really equipped to go into icy waters. Did make a few trips into those areas, but being very careful about how it interacted or didn't interact with ice. In terms of some factoids, they tried to core about 105 miles worth of material. They actually got 60 miles out, so about 60% success ratio, which is not bad for kind of just getting started in the process. 19,000 cores, multiply that by 4 to 6, because not all cores are ideal. That gives you an idea of the number of sections that were recovered. So again, keeping track of essentially the library type work for these was important. Deepest penetration about 1 mile into the seafloor, maximum penetration into the hard volcanic rocks, a little bit over 1/2 mile. Deepest water about 4.3 miles deep. And the total distance traveled in that 15 years worked out to be about 15 times around the Earth at the equator. So it wasn't all a trip around the Earth at the equator, but if you added up that mileage, it was about that far. In terms of OSU people who were involved, this is what I'm aware of. There could well be others. Someone who had gotten a master's at OSU in the late 50s, early 60s, then gone on and earned a PhD, and he was at ETH in Switzerland by the name of Ken Su. He was the co-chief scientist on leg 13, which got lots of publicity for a reason that we'll talk about in just a second. Peter Webb, who came to OSU about 5 years after leg 28, and Peter Barrett, who had gotten his PhD and finished up here probably 2 or 3 years before leg 28. They both sailed on leg 28. Our colleague David Elliott over here sailed on leg 36 in the South Atlantic. And if you want interesting stories about encounters with the Argentinian Navy when they came out and put the ship under lockdown for a few days, you can talk to him later. Almost all of us have interesting stories about things that happen when you're on the ship. And then I sailed on leg 86, and about 3 months after that, I came to OSU, bringing along several hundred samples, which were things that I worked on and my first sets of students worked on here. All right, major scientific advances. DSDP proved the geologically young age of the seafloor, which was crucial for confirming this, what was at one time was considered a pretty harebrained idea of plate tectonics and seafloor spreading. Without the results from the early legs of DSDP, that would still be considered a harebrained idea. The evidence that the Mediterranean Sea underwent a significant desiccation event, maybe not full drying out, but a significant desiccation event about 5 million years ago. That was actually an outcome of leg 13, which Ken Su was a co-chief scientist on. It recovered an intact section of the upper ocean crust, the volcanic rocks, demonstrated the significant amount of groundwater that flows through the seafloor. So some people talk about the ocean floor as the world's largest aquifer. Unfortunately, it's not fresh water and it's hard to access. So to humans, at least directly, it's not very useful, but in terms of things like chemical cycling, it is hugely important. And it also was its results were very important for helping us identify trends in Earth's climate, especially over the last 60 million years or so. These are both long-term trends, so over millions to tens of millions of years, and also what we talk about as orbital scale, which is changes at tens of thousands to hundreds of thousands of years. The heartbeat of the ice ages, if you've heard people talk about this, the so-called Milankovitch cycles. All right, so that was DSDP. Then in the mid-1980s, we transitioned from DSDP to the Ocean Drilling Program, ODP. And with that, we transitioned to the new vessel, at least new for us, the JOIDES Resolution. So this is the JR. We're going to talk about the JR quite a bit, so let's do a quick tour of it. It's 471 feet long. The drilling derrick is about 200 feet high. Its name, this acronym, Joint Oceanographic Institutions for Deep Earth Sampling, that was a consortium of US institutions that existed mostly during DSDP. It's long gone, but the name still hangs around and still is applied to the vessel. And in this case, the name Resolution, that was Captain James Cook's favorite vessel on 2 of his 3 voyages to the Pacific. And although we may know him for sort of colonizing, claiming territory for England, he actually did a fair amount of science. So that's why the term Resolution is carried forward. All right, well, we got the picture here, forward up here at the front of the ship towards the bow. There's the bridge up there. This part is all the accommodations, and I'm sorry that those of you online can't see my pointer. But if you go sort of to the aft end of those 2 orange things, which are lifeboats, that's about where the accommodations end. From the aft end of those 2 lifeboats back to where the drilling derrick is, that's the lab stack. There's a whole bunch of laboratories all crammed together. We've got the rig floor underneath the derrick, again with a moon pool down at the bottom. Back here aft of the derrick, between the derrick and the helicopter deck, is where the pipe is all stored. And there's an automatic conveyor belt type system that pulls the 90-foot long stands of drill pipe forward to the derrick. Then the people working on the derrick do their thing and assemble the drill pipe. All right, the JR actually started out life. It was built to do work in the oil industry. Original owners, when it came to work for us, were a company called Southeast Drilling Company, or SEDCO, and British Petroleum. So when the first time I sailed on it, it had not kind of been anointed as the JR yet. It was called the Sedco BP 471. It's gone through a series of different owners over the years. Now it has been owned for the last 10 or 15 years by a Norwegian company called Seam Offshore. And I have to say that has been an incredibly good thing for us and for the vessel, because those owners have been, for whatever reason, have been hugely invested in keeping that vessel running. This is not their bread and butter. Their bread and butter is doing other things for Seam. This is kind of a one-off in their portfolio, but they have been hugely committed to it, and it's been wonderful for us. Okay, 471 feet long. It does have this dynamic positioning capability based on the presence of thrusters around the ship. So in an extreme case, the ship can actually do a 360 without moving. It can spin on its axis. Or if the harbor master would let you, this ship can dock by walking sideways into the docking site. They will not let you do that. There has to be tugs, but it will do that. Now, there is a limitation though. In order for things to stay safe, particularly for the drill pipe to stay intact, the vessel cannot move more than 1% of the water depth off of vertical. So let's take an average ocean depth of 4,000 meters. 1% of 4,000 meters is 40 meters, basically half the length of a football field. This vessel has to stay within half of a football field length with no anchors down, using dynamic positioning of vertical. There are conditions when the waves get too high, the wind gets too strong, that you can't do that. Then we pull out of the hole. We call that poo, P-O-O-H, pull out of hole. And we wait on weather. And when the weather calms down, assuming that you had put in a re-entry cone, then you go get back into the hole and go back to work again. Ship sails with about 120 to 125 people on board. 65 of them are the crew. That's the people who run the ship, the people who run the drilling rig, people who cook your food, clean your cabins, and yes, they even do your laundry. But man, they're used to working with really dirty, greasy overalls. So when you say that they'll do your laundry, you got to be really careful what you give them, because it's going to come back shrunk and pink because the overalls are red. Then we have about 60 people on the science side. About 30 of those are scientists. The others are the lab technicians, operations engineers, and 1 or 2 education and outreach people. Here we have a picture of the rig floor. One thing to know about the JR is that it uses a drilling system that we call an open hole drilling. So there's the drill pipe, and that's it. There are other systems that exist with a drill pipe, and then there's a larger pipe called a riser that's around that drill pipe. That riser will also go down to the seafloor, get cemented in. It allows you to control conditions within the hole much better for both safety and for drilling, but the JR doesn't do that. So the debris that's being generated when you do the drilling at the drill bit, that gets flushed up the hole to the seafloor, hopefully. Sometimes it doesn't, and that causes problems. But it gets flushed up to the seafloor, and then it gets left there. So that's why this is sometimes called drill and spill, because the cuttings, the debris, get left as a mound on the seafloor. Assembling the drill pipe, this ship is incredibly fast. They can put together 600 meters per hour. So when we come to a site, if we're working in, say, average ocean depth, 4,000 meters, we know it's going to take them about 7 hours to assemble the drill pipe, another 3 to 5 to do some fine tuning of the systems. So within about 12 hours of getting on site, we're going to have core on the floor, and we're going to be getting ready to go to work. This crew has extensive coring experience. They are very good at what they do. Some of these people have been working on the ship since the beginning. This guy over here on the left, sorry, those of you in Zoom land can't see this, but the person who's closest to the top of the screen on the left, his name is Joe Atreed. Almost nobody on the ship knows that his first name is Joe. He's Bubba. And Bubba has been on the ship since it started drilling for us. And he is incredibly valuable as a resource for knowing how to get us the kind of core that we want. All right, they're very good at what they do. They also have the ability to put instruments into the borehole after the hole's been drilled. That's called wireline logging. We have a couple of people from Earth Sciences sitting over here who work a lot with wireline logs. If you're interested in knowing about that black magic, I mean, that really good science later on. And the ship can work in water depths up to about, for total drill string depths, lengths of 7 kilometers. That's the weight the derrick can carry. And we know from hard-earned experience that we don't do well if the water is less than 100 meters deep. We had some significant issues and accidents at times when we were drilling in shallower water. So we've learned we don't go there. All right, here's a cross section of the vessel. The working part for the science is in these various colors of sort of brown, orangish brown, green, and gray. The labs are primarily on the core deck and the forecastle deck, a few on the main deck, and then these holds that are labeled as the tween decks. Those are refrigerated rooms where the core is stored after it's been taken and until it's offloaded when the ship comes back into port. All right, we like to say the JR is a floating laboratory. So there are a lot of pictures crammed together, but I hope if you look at any one of those pictures, you notice there's a whole lot of instruments and a whole lot of computers. And you think about people doing dances with 1.5 meter long lengths of core. It can be like a ballet. But sometimes as you're going from one of these track systems, like we're seeing in the upper right, to another one of the track systems, you actually have to flip the core around. So there has to be coordination or core ends up on the floor, and that's not a good thing. We also like to say that the JR is a floating university. When I sail with 30 people, it's quite likely that I don't know at least 25 of them before I get on board. And I've sailed 9 times, and I tell students, I tell people who are thinking about sailing, every one of those 9 times has been like a postdoc. One time I sailed with a guy who was extremely good at the chemistry of the water that's in the sediments. So I basically got an intensive short course on pore water geochemistry. Other times it's people who are very good with the physical property. So it's an incredible opportunity. In the US, we try to sail at least 2 to 3 graduate students each time, because we're trying to build the capacity for our workforce to continue into the future. All right, so that was a quick introduction to the JR. Now let's go back to ODP. Maintained the standard of 2-month-long cruises, big science, but it got even more complicated with various parts being headquartered in various places. There was a new library facility stored for cores at Texas A&M. So all of those cores that were at Scripps had to be moved, and then all the new cores that were taken that were from the right geographic areas also went to Texas A&M. And then a number of technical advances, all of these allowing us to core in places we couldn't core before, or to get better core from places that we could already core in. About 650 sites were occupied. Again, predominantly low to mid latitudes, but with a bit more sort of wandering off into higher latitudes. 135 miles worth of core recovered and stored, 36,000 cores. Remember, then multiply that by 4 to get the number of sections. Deepest penetration into the ocean floor, 1.2 miles, deepest water, 3.6. Total mileage over ODP was 14 times around the world at the equator. OSU involvement, I sailed a number of times. Then between Peter Webb and myself, by my count, we had about 5 graduate students who sailed, and several tens of theses and dissertations with materials from either existing older expeditions or cruises or newer expeditions or cruises. In terms of major scientific advances, we did our first coring at submarine hotspots on mid-ocean ridges, identified past times of really, really large volcanic activity. You think about what's going on in Hawaii today, multiply that by, I don't know, David, 1,000. 1,000 times more active to create these things called large igneous provinces. First coring of things called gas hydrates. If you're interested in gas hydrates, and you should be, talk to Ann Cook over here because she's our resident expert on gas hydrates. Also, the first recovery of microbial communities from deep within the seafloor. When ODP started, the conventional wisdom was 10 meters into the seafloor was as far down as you'd find bugs. Now, as deep as we can core, there are bugs. And so big questions on how did they survive? You know, what are they? How did they evolve? How did they survive? And improved knowledge about certain aspects of Earth's climate, both long-term trends and also these orbital scale variations, and then even quicker events, which have potential impacts for understanding what might happen in our climate future. All right, then about the turn of the century, we go from ODP to the IODPs, IODP-1 and IODP-2. And these get more complicated because rather than using a single vessel, multiple vessels start to be used. So this is called multi-platform. All right, here's a quick introduction to the multi-platform. On the left, we have the JR. Already talked about it and the fact that the drill pipe goes to the seafloor. There's no other pipe around the outside. So it's riserless. Our Japanese colleagues built and operate a vessel called the Chikyu, which does riser drilling, where you have the drill pipe and then you have this outer pipe. What that does is allow you to circulate fluids down, wash out the cuttings, bring them all the way back up to the ship. You don't dump them on the seafloor. What you'll also notice in that middle diagram is this thing at the seafloor called a blowout preventer. The riser gets cemented into the seafloor, and you can then install a device called a blowout preventer. Think of it as basically a cork. And if the seafloor was a champagne bottle and it's getting shook up and you've got a bubble of gas that's going to come out, the blowout preventer is the cork that you cram into the hole, in theory, to keep that bubble down there. Now, for those of you who have paid attention to the Deepwater Horizon story, the blowout preventer did not do its job there. That was one of the issues. And that's why you then had a blowout and the fire and all of that. But in theory, at least, this provides safety and also allows you much better control on your drilling conditions. And then the third leg on our multi-platform stool is what are called mission-specific platforms. These are shown on the right. These are supplied by our European colleagues. And these involve going out and finding specific platforms, kinds of ships, other kinds of drilling system that can be used in places where either riserless or riser drilling won't work. So if we know the JR doesn't work well in less than 100 meters, if you're going to go very shallow, you get a jackup rig like they use for oil and gas drilling. The one that's illustrated here on the far right, if you want to go drill in the Arctic where there's lots of ice, you lease an icebreaker. And you put a smaller drill rig on that icebreaker, and then you can go into those ice-covered waters. So that's the idea of the multi-platform approach. All right, we have had to develop for our funding agencies science plans for IODP 1 and 2, both focused on 4 major themes. One is climate, one is deep life. This is the microbial life in the seafloor. Planetary dynamics, that's the story of volcanic activity, plate tectonics, and then geohazards. For example, what are the processes that cause large earthquakes at the trenches around the Pacific Ocean and generate very large tsunamis? We go to the Indian Ocean. This is what happened in the Banda Aceh situation in the early 2000s, estimated to have killed 200,000 to 300,000 people. We can be confident that something like that will happen off the coast of Oregon and Washington somewhere along the line. The only question is when. All right, the members who've been involved in IODP have sort of changed over the years. The 3 long-term components are the US, Japan, and a consortium of European countries. And there have been minor members who've come in, gone out, come in, gone out. So of the listing that's up here now, Brazil is no longer involved. Israel is no longer involved. New Zealand and Australia are a minor partner. So is India. South Korea is now out. China is also a minor member. All right, so the multiple platform approach, here we have pictures of them on the left, the JR, in the middle, the CHICU, and on the right, an example of the mission-specific platforms, in this case, working in the Arctic. Just below that, there's sort of a tally sheet of who's done what through ODP and then the various IODPs. ODP, we only had one vessel, that was the JR, 111 expeditions. ODP 1, the JR did 30 expeditions. That might seem low when you compare it to IODP 2. What I have to point out is that the JR was laid up for about 2.5 years doing a complete remodel in Singapore. I mean, everything was stripped out. The hull was redone, then everything was put back in. So that knocked about 2.5 years of operation out of that. But 30 expeditions in IODP 1, 39 expeditions so far in IODP 2. We have 6 or 7, I forget, expeditions still scheduled through the remainder of IODP 2. The JR has been and continues to be the workhorse of scientific ocean drilling. I don't think there's any way you can argue that. People who've been involved, we've got something like 6 folks, faculty members or research staff from OSU who've sailed during IODP 1 or IODP 2. By my count, something like 3 graduate students and lots of theses and dissertations. The CHICU, the vessel that can do the riser drilling, did 13 expeditions in IODP 1, has done 4 expeditions in IODP 2, but they've all been close to Japan. We have a couple of people, including one in this room, who've been involved with CHICU operations and a number of theses and dissertations. Mission-specific platforms, 5 expeditions during IODP 1, 4 in IODP 2. None of our folks have sailed or been involved, none of them who were active. A whole bunch of our alums have been involved in various mission-specific platforms. But I will say, the mission-specific platform operations, so there have been only a few of them, have been extremely high visibility. Was drilling in the Arctic in 2003, and then about 5 years ago, drilling into the Chicxulub impact crater in the Caribbean. All right, sites, again, mostly low to mid latitudes, but making our way into higher latitudes, especially with some of the mission-specific platforms. IODP 1 sites towards the top, IODP 2 sites towards the bottom. I've talked before about repositories. Let's go ahead and show you. Starting with ODP, we have 3 core repositories, one in Bremen in Germany, one at Texas A&M, and one at Kochi in Japan. Each of those repositories now has something close to 100 miles worth of core. In the upper right, you have a picture of a part of the Gulf Coast repository at Texas A&M. You'll notice that the upper half of those cores have red end caps. The lower half is black. That's archive half above, working half below. So those are the 2 parts of the core. It's split lengthwise. We preserve the archive half for as long as possible so that there's material for new generations to work on. In terms of the footprint of the Gulf Coast repository, was as you're leaving here, if you're not, if you don't think about it on a regular basis, take a look at the playing field area for the Woody Hayes training facility. The footprint of that repository is about the same as the footprint of the playing field. It's not as tall, but that's about the footprint. And these are all refrigerated at 4 degrees centigrade. Try to keep the cores as pristine as possible. So it is a huge infrastructure commitment to keep these going. All right. That was believe it or not, that was a brief tour of scientific ocean drilling. So how does the program operate now? And what does the future look like? So I would say, I will state it now and then I will show you data, that the scientific ocean drilling scientific community, and I stress scientific, is scientifically healthy, it's productive, and it's internationally integrated. So from the science side, the future for scientific ocean drilling looks good. Then comes the but statement. And here I borrow a line from Tom Hanks in Apollo 13, Houston, we have a problem. And in this case, we actually have 2 problems, depending on what length of time you want to think about. If you want to think about the next 3, 4, 5 years, we have a budget problem. You want to think longer than that, we have a ship problem because the JR is old. It's being maintained, but that's going to run out. So let's look first at how the program works today so that I can sort of reinforce or hopefully convince you of those statements I've made, and then we'll look at the problems. So I personally wish that this diagram was flipped around, but this is the way it's presented. And the reason I wish it was flipped around is because scientific ocean drilling is and always has been bottom up, community driven. So teams of scientists get together and generate proposals. Those proposals go into a review process that reviews the science that's proposed, the place where they want to do the work, and whether it's operationally feasible with the platform that they want to use. There's also safety thrown in there. But assuming that a proposal makes it out of SEP, the fastest I am aware of any proposal making it out of SEP is between 2 and 3 years. And there are some proposals that take 6, 7, 8 years to meet all the criteria to be sent on. But once a proposal gets out of SEP, then it goes to what's called a facility board, which handles the recommendations for scheduling and operations for each of the platforms. So there's a facility board for the mission specific platforms. There's a facility board for the JR. That's the facility board that I presently chair. And there's a facility board for the CHICU. Then there'll be a pool of proposals waiting to be scheduled at each of these facility boards. So when a proposal gets out of SEP, in the JR case, it may sit at the facility board for 5 to 6 years because the vessel doesn't just run from one ocean to another. It works in one ocean for several years, then it goes to another one, then it goes to another one. So there's a lot of patience involved in this. Now, just to give you a little bit of insight to the budget model problem when we get to that, I've got some numbers at the bottom. The Europeans' annual budget for operations is about $10 million. For them to put on an expedition is somewhere between 10 and 20. So how many can they put on in a year? At most 1, and if things don't go well, not even that. JR operations budget about 58 million, costs about 10 million to put on an expedition. Notice that's in green. The Japanese, the CHICU, they actually have to go earn their money from industry work. What they get from the government only pays what it takes to keep the ship on the dock. If they want to leave the dock, they have to earn the money to do that. They do that by industry work. They earn that at a rate of about $2 to $5 million per year. For them, an expedition is $10 to $20 million. How many expeditions can they put on per year? Yeah, not many. So maybe you can start to see that there are some imbalances in here. And that comes up in the budget problem. All right, I said that the scientific ocean drilling community is scientifically healthy. We have 92 proposals in the system right now, distributed between the 4 various parts of the science plan, but 92 proposals. At most, we're able to drill, let's say 6 a year. This is 15 years worth of drilling that's already in the pipeline. If we look at how many have made it past the review at SEP, we've got 53. So that's almost 10 years worth of drilling that's just sitting at the facility boards. This is why I say scientifically, this is very healthy. We've got science to do. The question is, do we have the facilities to do it? All right, and no big surprise, the JR has been the workhorse for the proposals that are in the system. The JR continues to be the workhorse. It's very good at what it does. No, it doesn't do everything, but man, it is really good at what it does. All right, so scientifically healthy, I hope I've convinced you of that. Productive. The publications people at Texas A&M have compiled information. This is shown number of publications in various journals, ranked by their impact factor. This is only the top 15 or so. And I think this is a pretty impressive number. Over the 50-ish years of scientific ocean drilling, 29,000 papers that they're aware of, with over 11,000 unique first authors. We're now on about the 3rd generation of scientists who have worked through their careers in this set of programs. So scientifically healthy, productive, internationally integrated. The publications folks created this co-author network Shows that lots of interrelationships among our major partners and also minor partners and even countries that aren't even part of the program, have never been part of the program. So that repository of all those cores, once you're a year past the expedition where they're collected, anybody anywhere in the world can request samples for a study. That's how you end up with people from countries that have never been part of the program, Indonesia, Morocco, being listed as authors on these papers. And we are well positioned for the future. The international community has spent the last 3 or 4 years generating essentially the next science plan, pointing out to 2050. So scientifically, I think we have our ducks in a row. So Houston, we have a problem. In the short term, it's a budget model problem. In the long term, it's a ship problem. So let's take the short term first. The JR's annual budget is about $58 million, as I mentioned before. Of that $58 million, NSF contributes 48, the Europeans contribute 7, the Japanese contribute nothing. The balance is made up by contributions from minor partners and some savings accounts. And those savings accounts are depleted. We're about at 0 on those now. According to the memoranda of understanding that were established for IODP2, the US, the Europeans, and Japan each get equal numbers of berths on all the platforms. So on a JR expedition, there's about 8 US scientists, 8 Japanese scientists, 8 European scientists. That divvying up was all predicated on an expectation from our partners that the CHICU would operate 1 to 2 expeditions per year, and the mission-specific platforms would operate 1 to 2 expeditions per year. And the US doesn't pay to those. So the US subsidizes others on JR in order to get berths on other platforms and vice versa. But as we saw before, the number of mission-specific platform expeditions, the number of CHICU expeditions are nowhere close to what was expected. And so the bottom line is there's a real cost differential. The cost to the US to sail a scientist has ended up being 4 to 10 times the cost for our partners. As you might imagine, NSF is not excited about seeing this continue into the future. And so the JR could actually be extended for another 4 years because its environmental certification is valid through 2028. But this budget arrangement ends at the end of 24. So about a year ago, NSF requested indications of interest from our partners for extending the JR, but on an equitable cost per berth. And the number they cited was $470,000 per berth. So let's call it 500,000 per berth. Unfortunately, our partners came back and said, well, we're kind of interested, but we can't make firm commitments. I mean, if you've gotten used to these deals, how quickly are you going to say yes to a big bump in price? Probably not very fast. So we presently are in a situation where NSF is trying to sort out. You can't run the JR full-time on $48 million a year. So do you run it part-time? You demobilize the JR and use the money in some other way? Or is there some other way to deal with this situation? Start buying lottery tickets. I don't know. This is what NSF is thinking about. We are still awaiting NSF's decision on whether or not the JR will be extended. And 30 minutes before I came into here, I got an email from our program manager at NSF organizing a phone call for Monday afternoon. So the word may come down. Whether it's good, bad, or indifferent, it will be useful to have a decision. Meanwhile, our partners are making plans to move ahead. The Europeans and the Japanese are talking about an alliance, continuing to use mission-specific platforms and the CHICU. We don't say this in polite company, but it's not clear where they would get any extra money. So the question is, can they do more during the next whatever it is than they've already done with a budget model that's been proven to be broken. Also, the Chinese have been building a vessel. This is a screenshot taken from a video posted in December. Their vessel is about ready to go into the water. They look for it to be operational by 2025. Now, what we've heard is that it may be available for scientific ocean drilling as opposed to industry work 4 months a year. They advertise that it is an ultra deep water research drilling vessel, but based on some of the characteristics that we've heard about, it is really unclear that it will be able to do what they are promising. So this is going to be a case of the proof is in the pudding. There have also been some issues where NSF has interacted with their Chinese equivalents, and certain trade back and forth about data and samples have not been met. So there are questions about whether they will follow international norms for cooperation. All right, that's the short-term issue. The long-term issue I referred to earlier when I was talking about the GLOMAR Challenger. A new US vessel, whether it's a new build or a long-term lease, is likely going to be costing $1 billion or more. And in that case, it becomes what's called an NSF major facility. DSDP, a major facility, 2 years from plan to operation. In today's world, 10 to 15 years on the short end. That's if NSF decides to invest. And there's this thing that's gotten thrown into the middle of what's called a decadal survey. That's the decision about whether or not to move forward on this is going to be based on the outcome of that decadal survey. So there are many uncertainties. So what do we do in the meantime? One possibility is run the JR as long as possible. That puts us into the budget model problem. Second, possibly fund US scientists to work on the other available platforms. Not clear where that money would come from within NSF right now. That's also part of NSF's discussions. And there's a lot of interest in what are informally referred to as virtual expeditions. We've got 450 miles of core. I don't even know what the modifier is that you would use for how much data we have. It's terabytes, petabytes, I don't know. Derek and Ann would have a better idea. Huge quantities of data. So are there ways to do science going back and looking at existing core, mining existing data? This goes into things I have no idea about, but that's being considered as well. So all I can say at this point is, if only the future of scientific ocean drilling was as clear as the weather that they saw on the last expedition when they were drilling in Santorini in the Aegean Sea. Maybe after Monday, it will be clear. But at the moment, we have uncertainty on many different levels. So, thank you. Question.
Thank you. It was really shocking or obvious to see no involvement in any of this from the largest country in the world, which is Russia. What's going on there? Do they have their own drilling ship?
No, they don't. So Russia was involved. I can't remember whether it was involved in DSDP, but I know it was involved during ODP, because one of the expeditions that I sailed on during ODP actually had a Russian co-chief scientist. There were some concerns early on about proprietary nature of the dynamic positioning systems. And so there were times when Russian scientists were able to sail, but they actually could not go into the room where the dynamic positioning system capability was. The Russians chose not to be involved in IODP 1 or IODP 2. So no, that's been their choice.
So they would have been welcome during all those years.
I would say they would perhaps have been welcomed up until a year ago.
Okay, well, yeah.
And I say that because there was actually one of the mission specific platform expeditions was supposed to be happening this summer to go back into the Arctic. And it's officially postponed, but it's effectively canceled for two reasons. One was that one of the 3 icebreakers was supplied by a Russian company, and you only had to trace back one step from that, and you ended up at the Russian government. And the second issue was that the evacuation routes, if there were any medical evacuations, had to go through Russia. And given the present geopolitical situation, that was completely untenable.
And the second thing is, as a complete amateur who understands nothing about this except what you've told us, how does the drilling pipe work? Is there a solid, like my hand drill, is there a solid drill at the bottom that's drilling a hole and that material is going up the hollow pipe? And or how do you get a core? What is a core? Is it
Sure.
just a solid piece of
Yeah,
rock?
sorry.
or-
So a core is a long cylinder of sediment or rock. If it's relatively soft, it has to be brought up in some kind of a plastic tube, because if you're trying to lift something soft that way, it's just going to collapse. So the drill pipe, about 5 inches, 4.5 inches across. If you just want to make a hole in the ground, you put a bit onto it that's kind of like what you use for drilling into wood. And then all you get out are the cuttings. But in our cases, if we want to actually get a core, then we have a number of different ways to essentially cut the outside while leaving the inside intact.
Okay.
And then at various times after you've advanced down, let's say 9 meters, there's a way to grab that remotely and pull it back to the surface.
Amazing. Thank you.
Yeah.
Other questions?
I'm sure there are, but what are the protocols when you're pulling up a deep ocean core that has microbes in it and you don't know what they are? Could they release into the environment? Same kind of protocols you have when you come back from outer space.
Yeah, so I think this whole field of working on the subsea floor microbiome has evolved. So when the first work was being done on this, it was just a surprise that there was anything there. Now, particularly for the expeditions that have significant microbiology objectives, then there are all kinds of clean handling protocols. I have not sailed on any of those expeditions, but there are clean handling protocols to try to maintain the samples in pristine a condition as possible from the time that they leave their original home down in the seafloor to coming to the deck, to going into a lab, to going into storage. Yeah, and in terms of the sort of space use on the vessel, it's been that increase in the need for certain kinds of handling, certain kinds of refrigerators, certain kinds of hoods for the microbiome side that has really put some stresses on the system, because we don't create new space in the ship. If you're going to divert a bunch of space to the microbiology work, it has to be taken from something else. Did that answer your question? Now, yeah. There you go. Yep. Now there's a completely separate side to answering your question, which is if the core is taken in international waters versus if it's taken within one country's territorial waters. Because I know nothing about details. You may, if I say Nagoya Protocol, this may be something that some of you know about. There are protocols for how microbiological analyses and materials are handled. And so for certain countries, if you are going to be coring in their territorial waters, then there has to be a pledge to follow the Nagoya Protocol. I only know about that because it gets mentioned. I know nothing beyond that in detail. But the whole issue of getting clearance to work in territorial waters has become much more difficult. It used to be really easy. Now there are some places that you simply cannot go because you can't get clearance. And then there are places you don't go because you worry about pirates.
Other questions?
Yeah, this is all like sci-fi for me, so pardon if this is like one of those questions.
No.
But you mentioned that the archival storage of the core samples is kept at a particular temperature, particular pristine. What's the temperature we're talking about in the core? Does it ever get warmer? I mean,
So
what are
some
we
of these
talking
cores,
about?
when they are brought up from the seafloor, may have been warmer, but the storage is at 4 degrees centigrade, which is about 40 degrees Fahrenheit. And there are some people who are starting to question that, but there have been two primary reasons why people have wanted to store cores, and they get wrapped in sealed plastic in these refrigerated rooms. One is that you want to try to keep them from drying out because there are certain properties of the sediments that change once they dry out and you can never get them back, even if you submerge them in water. The second has been to try to minimize microbial activity. But I can tell you from sampling parties that I've been to 6 months after the core was taken, Derek and Ann may say the same thing, even 6 months after, stored in a refrigerated room, there's already mold growing on the surfaces of the cores. You know, you probably ought to be wearing a mask when you're doing those sampling parties. So there are both physical and chemical reactions that you try to keep from taking place, and then also trying to keep the mold down. But there are people now starting to question, because of the cost of maintaining those refrigerated rooms, you know, it's a cost benefit question. Is the gain from keeping them refrigerated really worth what it takes?
I have a question.
Sure.
It's the budgetary,
Mhm.
the answer that you're looking for on Monday. And what happens if the answer is a yes? What happens if the answer is a no?
So if the answer is a yes, there are several versions of yes. The ideal yes would be that NSF would come back and say, we're going to keep supplying the $48 million a year. And oh, by the way, from a different pot of money, we found the extra 10 million. In that case, we just keep operating it. Now, the program is ending. So for example, the advisory board that I chair, officially it goes away when IODP2 ends. But NSF could say, we want you to continue, or we want a similar body to continue. You know, if the best of the best answers comes back, we basically do business as usual. And one would expect that if the US is now fully funding, all 30 of those berths for scientists on every expedition are going to be for US scientists. So we could be sending 10 or 15 graduate students out on each expedition. And this actually has been one of the selling points that we've tried to put out there. You know, NSF is pushing big on workforce development. This is workforce development, you know, just keep operating the vessel. If it's a yes for 48 million, then it's really NSF's decision how they want to handle that, whether they want to continue using the vessel, but on a part-time because they have to renegotiate with the vessel owner, and chances are good that they won't get a deal that's quite as favorable. Yeah, and then we go on. If there's no money, then we start looking at virtual expeditions. I think that's really what we're left with.
It seems to me in terms of that no answer. And all of the work that's going on, et cetera, what does that mean? I mean, things just stop? And what is, and in other words, what does it begin to mean for the environment?
You mean like the physical environment of the oceans or the work environment of the people?
I mean, the physical environment of the ocean.
So the physical environment of the oceans, we actually do have to do some monitoring while we're drilling, depending, particularly for some countries, after you've drilled in their territorial waters, they require you to come back and do monitoring after the fact. The environmental footprint of this vessel's operations, I would say, are trivial compared to the environmental footprint of commercial shipping, even tourists going to Antarctica, things like that. So on that side, I think it would be nothing recognizable. Yeah. In terms of the work environment for our community, it'll be, I would approach using the word disaster. Yeah, we have some, I'm sorry, from my perspective, we have some early career people. I know they're now sort of mid-career people, but we have folks who are looking at using this resource for probably the rest of their careers, and they're training students who've been looking at this, and to take that away will have significant impacts.
Well, there are two other things.
Could you tell us, as a scientist, what you have discovered and learned on your voyages with the JOIDES Resolution?
Sure. So
Briefly.
sure. So, and I have some colleagues, some of whom I don't mean to insult, but others who I know have shared this experience. And I think the primary lesson that I've learned and that I try to pass along to students from all of this is, when we go out to drill, this goes back to the whole what it takes to get an expedition drilled. You propose the science, but you also have to propose the where. And in order to get the where approved, you have to provide some background information. And the analogy I would use on this, that background information is kind of like an X-ray or an MRI. We have a variety of techniques that allow us to look into the seafloor. We can use similar techniques to look into the ground right underneath us. And what those do is give you what are essentially echoes coming back from boundaries. And there are lots of people who will build lots of stories based on what they think the ages of those echoes are. And you don't know till you get there. So I've been on expeditions where people had suggested that a particular echo represented something that was about 60 million years old. It turned out being 1.3 billion years old. That's a significant difference. So ground truthing, you know, being able to ground truth in my experience is essential. We can build stories from there about a whole variety of things, but the ground truthing, and I say this as somebody who works on the core, not on some of the imaging stuff, you know, it is essential.
There's a follow-up. How about your science? What have
Yeah, so a fair amount of my science has been focused on trying to look at the history of glaciations. And what I think we've learned, I speak of me as part of a much larger community, is that it's never as simple as we think it is. Now, even in today's world, we talk about a warming world, 90% of glaciers are retreating, but there are 10% that are advancing. You look at the details of glacial histories in an area, there's always that degree of complexity.
Got another question.
Yes, so with reference to the different locations where scientific ocean drilling, it operates all around the world, how does the permit thing works? I believe wherever they are drilling, they have to ask for permission from the neighboring countries or the nearest country that we are drilling in your territorial
If
waters.
it's
So how does that work?
territorial waters, if it's international waters, it's no big deal. You don't have to get clearance from anybody. But I'm sorry, I interrupted you. Go ahead.
Yeah, so is there a central governing body that approves that permission, or is it just for the specific country where they are drilling?
It's done country by country. Yes, and I can tell you that the administrative office for the JOIDES Resolution, which is at Texas A&M, about 3 years ago, hired a new person to do nothing but deal with clearances. Because it used to be an add-on to somebody else's job, and it was becoming such a time trap that they had to have one person who is now completely devoted to working to get clearances.
And how long does it take usually for those clearances?
That's very variable. And it varies a lot depending on the country and how well defined the path to getting the clearance is. There have been situations where where the clearance officer has started trying to get the clearances, and then basically gets into a ping pong game between about 3 governmental ministries and just goes around that loop over and over and over again. And there have been times when expeditions have had to sit in port for up to a week trying to get the final okay to go. Because if you go without it, then you're in a Professor Elliott situation, and the Argentinian Navy comes out and sits on the doorstep while you're trying to shift some drill pipe around. So it is a big issue. And there are some countries that have now essentially made it impossible to get clearance. Yeah. And there's some very good science proposed for their territorial waters, and we just have to tell the proponents, we can't schedule your expedition because we know it's not going to be able to go.
What are the criteria on which you decide where you're going to go and drill next? What goes into that?
Yep. So the question was having to do with scheduling. And our approach, and I speak for the JOIDES Resolution in this case, our approach to that changed about 8 years ago in response to the results of the last decadal survey of the ocean sciences. Because like a number of other large programs in the ocean sciences, ocean drilling, the operation of the JR took about a 20% budget cut, but we were still expected to do very well, do a lot of science. And so this probably should have been done before. But before those results came in, it was not unusual for the ship to be in one ocean for maybe a half a year, then go through the Panama Canal and be in the Pacific. So there was a lot of time spent on transit. As a result of this outcome of the last decadal survey, we've adopted a regional track planning. So we tell the community the ship's going to stay in the Atlantic for the next 4 years. If you have a proposal for the Pacific, that's great. When we get to the Pacific, we'll think about it. We then depend on the operator, the people at Texas A&M, to give us some options that minimize the transit time, the travel time, and maximize the time on science. And at the same time, we take the SEPS evaluations because some proposals are passed forward with a ranking of 1, some with a ranking of 2. So we're trying to maximize the science that we get while minimizing the lost time and expense of things like transits. So it's kind of, it's sausage making, but we're guided by input from the experts.
Other questions? Thank you so much for
Okay, thank you.
very insightful presentation.